What's going on, all of my healthcare brothers and sisters? I hope that you are having a wonderful day. The ATI-TEAS science portion of the test is one of the most important portions of the version 7 ATI-TEAS because it discusses a lot of different things that were not on version 6. So this in-depth guide looking specifically at chemistry is going to help you pass your test the first time. We'll discuss the type of questions that you're going to see in the test and offer tips and strategies on how to pass them. Let's get started. So let's take a closer look at the objectives for chemistry. On the test, there is going to be a total of 8 questions out of the 44 questions for the science portion. And what you will need to know is the basic atomic structure, physical properties and changes of matter, chemical reactions, conditions that affect chemical reactions, properties of solutions, as well as acids and bases. So we begin by looking at our first objective, and that is recognizing basic atomic structure. And what better way to kick it off than looking at the different parts of an atom? Atoms consist of structures within the nucleus containing protons and neutrons. Electrons orbit around the nucleus in shells. So as we begin, a proton is a particle with a single positive charge. When you're trying to remember it, think proton, positive charge. Whereas our neutron actually has a neutral charge, right? It has no electrical charge at all. So proton, positive charge. Neutron, neutral, no charge. Those little tiny circles that are orbiting around our nucleus is known as electrons, and they have a negative charge. And what's interesting about them is they are about 2,000 times smaller than our proton. So when we're looking at different types of elements, we can determine what kind of element it is based on the number of protons found within the nucleus. So for example, carbon has 6 protons. As we move forward, isotopes are atoms of the same element that have a different number of neutrons. So for example, carbon-12 would have 6 neutrons because we know that there's 6 protons, right, in carbon. And carbon-14 would have 8 neutrons because, again, that proton number doesn't change. So carbon-12 and carbon-14 are considered isotopes of carbon. Something else that you're going to need to know is atomic mass. And the atomic mass of an atom is the total number of protons and neutrons. As electrons are so small, they really don't make up any determination when it comes to the atomic mass. So if we add our protons and our neutrons together, we can get the atomic mass. So for example, carbon-12 is 12, right? We have 6 protons and 6 neutrons, making the atomic mass 12. When you're looking for the atomic number, that's the number of protons in an atom. So again, as we know, carbon has 6 protons, making the atomic number 6. Lastly, atoms can be positively charged, negatively charged, or they can be neutral. This is determined again by the number of protons that are found within the atom. If there are more electrons than protons, then the atom is going to be negative, right? We have more negative charge than we have positive charge. Whereas if we have more protons than electrons, the atom is going to be more positively charged, right? We have more positive charge than negative charge. If the number of protons and electrons are equal, then the atom will be neutral. So let's talk about some good old-fashioned ions. Ions are atoms that have gained or lost electrons and as a result have a charge either positive or negative. So for example, traditionally sodium is made up of 11 protons, 12 neutrons, and 11 electrons. So as we know, we have 11 protons, 11 electrons. This is a neutral atom, right? They're the same number. When sodium loses one of its valence electrons in its outermost shell, then it becomes a cation because it has a positive charge. Remember, there's more protons than there are electrons, making it more positive. Cations are atoms that have lost one or more electrons and have a resulting positive charge. Whereas anions are atoms that have gained one or more electrons and are resulting in a negative charge. When an atom gains electrons, it usually happens within its most outer shell. So for example, chlorine has 17 protons, 18 neutrons, and 17 electrons. When chlorine gains an electron, it becomes an anion because now it is more negatively charged. Now we're going to take a closer look at something that mixes everybody up on the ATITs, and that is the periodic table of elements. The periodic table of elements is a chart that shows how elements are related to one another. So as we take a look at the chart behind me, the elements are organized by increasing atomic number. The columns that you're found, the up and down, are considered groups on the periodic table. So each column is considered a group. Whereas the rows, that's your horizontal lines, your rows are considered periods. There are a few elements that don't fit perfectly into the periodic table, and these are called transition elements or melatoids. You can actually see them down here at the bottom. The first two rows of the periodic table, way at the top, are the alkali and the alkaline earth metals. These are considered the active metals. The middle of the periodic table are considered the reactive metals. Okay, so first two rows, you've got your active metals, and then everything in the middle is considered your reactive metals. The elements on the far right, way up here above my head of the column, are the noble gases of the periodic table. They are considered the inactive gases. There are types of elements that are determined by the protons that are found within the nucleus. The groups on the periodic table represent how many valence electrons are found within the atom. So the columns of the periodic table go from left to right in order of increasing atomic number. So the first group, way over there on the left, only have one valence electron. The second column, group 2, has 2 valence electrons, and so on. The rows go from top to bottom in order of increasing atomic number. The first row, way at the top, has 2 valence electrons. And the second row, period 2, has 8 valence electrons, and so on. I actually included a little table way over here on the end where it shows you how that's broken down. To identify the number of electrons or protons of an element, you must look at the integer shown on the periodic table. The integer is the element's atomic number, which is usually shown as a whole number without a decimal. The atomic mass of the periodic table is shown as a decimal to account for the element's various forms of isotopes. So let's take a closer look at orbitals. Orbitals are areas where electrons are likely to be found and are different to accommodate the different electron numbers. So we begin by looking at our s orbital. That is more of a spherical area that surrounds the nucleus. The orbital is allowed to have a maximum of 2 electrons at a time. That's it. That's the max that it can have. Then we have p orbitals, and these are more of like a dumbbell-shaped type of orbital, and with these, they can have a max of 6 electrons at a time. Next, we have d orbitals, and that's more of kind of like a flower-shaped type of orbital that surrounds the nucleus. And these orbitals are allowed to have a max of 10 electrons at a time. And then we have f orbitals. These are really irregularly shaped areas that surround the nucleus, and these particular orbitals can have 14 electrons at a time. So when you're looking at this, just think 2, 6, 10, 14. That's kind of how I remember it when I am trying to remember the types of orbitals and how many electrons that they have. The number of orbitals an element has is the same as the period number it has on the periodic table. So for the first period, remember periods are our rows, they have 1 orbital. The second period has 2 orbitals, and so on. The orbitals are filled in order of increasing energy. So the s orbital is always filled first, then the p, and so on. So we've been talking a lot about electrons, and we've been using the word valence electrons. What the heck does that mean, right? So valence electrons are located on the outermost shell of an atom, readily available to participate in chemical reactions. Elements are the most stable when they have a full valence shell. So again, I included that orbital shell down here in the bottom of your screen to let you know each orbital should have these many things in their shells, right? These many electrons. So elements such as helium have a full valence shell and they are extremely stable. Other elements such as sodium has only one valence electron in that shell. These types of atoms are less stable and they're readily able to give up their electron in order to achieve stability for that particular atom. Next, we're going to talk about ionic and covalent bonds. Ionic bonds are formed when atoms trade electrons in order to achieve that stability. So for example, when sodium and chlorine form an ionic bond, sodium gives up one valence electron to chlorine. And you can see that in my little chart that I have down here. See how sodium had this one little valence electron? It gave it up. So now sodium is more of a positively charged because we gave up our electron. We have more protons than electrons. And chlorine is now more negatively charged because we gave up our electron from sodium to chlorine. So now it has more electrons than protons, making it more negatively charged. Whereas with covalent bonds, these are formed when atoms share electrons in order to achieve stability. So for example, when two hydrogen atoms form a covalent bond, they share that one valence electron in order to achieve that stability. In order to determine if a bond is ionic, covalent, or compound, you must look at the electronegativity that the atom has and what it's involved in. The electronegativity of an atom is measured of how strongly it attracts electrons to its shell. The higher the electronegativity, the greater the atom's attraction to electrons, right? So atoms with high electronegativity, such as chlorine, tend to be more ionic bonds, whereas atoms with low electronegativity, such as hydrogen, tend to form more covalent bonds. Next, we're going to start looking at physical properties of matter, and we're going to look at mass, volume, and density. So matter is anything that has mass and occupies space. Physical properties refers to the different properties of a substance that can change their state without changing the identity of that particular substance. So for example, water can exist in 3 different states. It can be solid, it can be liquid, and it can be a gas. The states of matter are determined by the physical properties of a substance. So for example, mass is the amount of matter in an object. It is measured by the inertia of an object and is measured in grams. So for example, a paperclip has a mass of about 0.01 grams. Volume is the amount of space an object occupies and is usually measured in liters. And density is the mass of an object divided by its volume. It is measured of how much matter is packed into a given space and is measured by grams per liter. See, we just kind of combined them there. Not too hard. The density of a substance can be affected by its temperature. So for example, water has a density of 1,000 kilograms per meter at room temperature. However, when water is heated, its density decreases and it expands. When a substance matter changes, the physical properties also change. So states of matter. The most common states of matter are solid, liquids, gas, and plasma. Solids have a definite shape and volume. They are the least compressible state of matter as molecules are tightly packed together in that tight pattern. Liquids have a definite volume, but they take the shape of whatever container that they're in. They are more compressible than solids as molecules are not packed together as tightly. Gases are neither a definitive shape nor a volume. They are the most compressible states of matter as molecules are farther apart from each other. And plasma is the state of matter that is often found in the stars. That is the gas that is ionized, meaning that electrons have been stripped from the atom. The phase of a substance is dependent on 2 conditions: temperature and pressure. Temperature is the measure of the average kinetic energy of the molecules in a substance. The higher the temperature, the more energy the molecules have. More particles of matter move apart, and the more space that they're going to take up. Pressure is the measure of force exerted on an object by the surrounding atmosphere. The higher the pressure, the more the molecules are forced to come together. The physical properties of a substance can be affected by the changes of temperature and pressure. So for example, water can exist in 3 states. We talked about it: solid, liquid, or gas. The state of water is determined by the temperature and the pressure. If the temperature is increased, the molecule of water will move faster and take up more space. This will cause the water to change from a solid to a liquid. Whereas if the temperature is decreased, the molecules of water will move slower and take up less space. This will cause the water to change from a liquid to a solid. If the pressure is increased, the molecule of water will be forced together. This will cause the water to change from a gas to a liquid. And then lastly, if the pressure is decreased, the molecules of water will be forced further apart. This will cause the water to change from a liquid to a gas. So chemical properties of matter refer to the ability of a substance to change its identity. This can happen when the substance undergoes a chemical reaction. These changes can include condensation, evaporation, sublimation, deposition, melting, and freezing. So beginning with condensation, this is the process of a gas changing to a liquid. This happens when the molecules of the gas slow down and move closer together. Evaporation is the process of a liquid changing to a gas. This happens when the molecules of a liquid gain more energy and then they break away from the surface of a liquid. With sublimation, this is the process of a solid changing to a gas. This happens when the molecules of a solid gain enough energy to break away from the surface of that solid. With deposition, this is the process of gas changing to a solid. This happens when the molecules of the gas slow down and then they start to move closer together. Whereas with melting, again, this is the process of that solid changing to a liquid. That's probably one of the most easiest ones to remember. This happens when the molecule of the solid gains enough energy and breaks away from each other. And then lastly, freezing, another good one to remember that you already know in real life situations. Freezing is the process of a liquid changing to a solid, right? This happens when the molecules of a liquid lose enough energy and they tend to stay together. These changes between states of matter are reversible. This means that the process can be reversed and the substance will change back to the original state. So for example, water can be evaporated and then condensed back to a liquid. Or a substance can be melted and then frozen back into a solid. Now we're going to move on to another objective, and that is describing chemical reactions. And we're going to kind of go over some things that we had already discussed to help you understand what's happening with chemical reactions. So beginning with valence electrons, in order to understand them, it's really important to know these things. Valence electrons are the electrons in the outermost energy level of the atom, right? They sit on those outermost shells. They are the electrons that are involved in chemical reactions. The number of valence electrons in an atom determines how it is going to react to other atoms. So atoms can gain or lose electrons in order to achieve that full outer energy level and stability, right? That's what these atoms always want, is they want to be stable. When this happens, the atom will form a chemical bond with another atom. So for example, when 2 chlorine atoms form a bond, each atom will have gained 1 valence electron. This is because chlorine has only 7 valence electrons when they should have 8. And just a reminder in regards to ionic and covalent bonds, these are the 2 different types of bonds that you are going to see. Ionic bonds are formed when atoms gain or lose valence electrons. They're either taken or they're given away. And covalent bonds are formed when atoms share valence electrons. Ionic bonds are usually formed between a metal and a nonmetal. So for example, sodium and chlorine form ionic bonds. Whereas covalent bonds are usually formed between 2 nonmetals. So for example, carbon and oxygen form a covalent bond. So now we're going to get into the nitty-gritty and we're going to start looking at chemical reactions. So chemical reactions can be represented by chemical equations. Chemical equations are written using symbols and formulas, and the symbols represent the elements that are going to be found in that reaction. So, the formulas represented in the compounds of reactions are reactants, arrow to the right, products. So the reactants are the substances that are involved in that reaction, and then the products is the new substances that were formed because of that reaction. So for example, let's take a closer look at a combustion reaction. Combustion is the type of reaction that happens when a substance reacts to oxygen to form either carbon dioxide or water. So the chemical equation that we have here on our slide is C6H12O6. That is the substance of sugar. Plus, we have 6 oxygens, 6 O2. You see our little arrow? So on the left-hand side, we have our reactants, and on the right-hand side, we have our product, okay? So these two reactants, when put together, are going to create a product of 6 CO2, so we're going to have 6 carbon dioxide atoms, and we're going to have 2 H2O, 2 water atoms. In this equation, like I said, C is the element of carbon, O is the element of oxygen. We talked about the element of sugar, and we talked about the element of oxygen that we found on the reactant side. We also talked about what it created. The arrow in the equation means react to form. That is what that arrow means. So in this equation, the reactants are carbon and oxygen, and the products are carbon dioxide and water. Now we need to understand how we're going to balance chemical reactions. A chemical equation has to be balanced on both sides. This means that there needs to be the same amount of atoms on the left side as there is on the right side. So for example, the equation for combustion of methane is CH4 plus CO2, and then our product on the other side, CO2 plus 2H2O. In order to balance this equation, we need to add a coefficient in front of each compound. A coefficient is the number that is placed in front of a symbol or formula in order to multiply it. Let's take a closer look at a different chemical balance and break it down on how this is specifically done. Now let's take a closer look at our own equation. And what we have here is we have H2O yields H2 plus O2. Now when you're taking a look at this, it doesn't make a whole lot of sense, and I'm going to show you why. When you read it, it's going to read as the compound of water is broken down by hydrolysis to yield hydrogen gas and oxygen gas. So on our reactant side, we have 2 hydrogen atoms, right? That's where we get the H2. And we have 1 oxygen atom, right? That's that one lonely little O that's right there. This is supposedly going to yield, that's our yield here, 2 hydrogen atoms, right? We know that makes sense. We have 2 on the left, 2 on the right, but we have 2 oxygen on our product side, right? 1 oxygen and another oxygen. So when we're looking at this equation, it is not balanced. How do we balance it? By adding a coefficient. So the coefficient is the number that is placed in front of the symbol of a formula in order to multiply it. So we need to get 2 oxygens on our reactant side in order to make our product side make sense. So we do this by adding the number 2 in front of our reactant. Now, this makes a little bit more sense, right? We're going to have 2 oxygens on our reactant side and 2 oxygens on our product side. However, by adding that 2, we have also doubled our hydrogen ions. So now we have a total of 4 H2s, right? Or we have a total of 4 hydrogens, 2 oxygens on the reactant side, but now we only have 2 hydrogens and 2 oxygens on our product side. So again, how do we balance this out? By adding our coefficient to make it make sense. So our oxygen is good. We don't have to do anything else with our oxygen. However, our hydrogen is not. And we are going to add the coefficient 2 in front of our H2 for it to make sense. By adding that, we have now added 2 more hydrogen ions. And when we take a look at this, we can see that our left is equal to our right. So now we have a balanced equation of 2H2O yields 2H2 plus O2. So moles. Moles are the unit that is used to measure the amount of a substance. The mole can be measured by the number of atoms, the number of molecules, or the mass of a substance. The mole is used in a chemical reaction because it allows us to calculate the amount of each substance that is needed in order to complete the reaction. So for example, let's say we want to know how many moles of oxygen we have in order to react 1 molecule of methane. You can see our equation down here for the combustion of methane. CH4 plus O2 yields CO2 plus H2O. The equation for the combustion of methane, as you can see, has 1 mole of methane, CH4, and we need 1 mole of oxygen, O2. This is because there are 4 atoms of carbon in methane, that's that CH4, and for every 1 atom of carbon, we need at least 2 atoms of oxygen. So in order to react 1 mole of methane, we need to have 2 moles of oxygen. So now we're going to move on to conditions that affect chemical reactions. And there are many, many different factors that influence reaction rates. The rate of a chemical reaction is the speed at which the reactant is converted into products. So a catalyst will speed up a reaction. There are several factors that can influence the rate of chemical reactions, including endothermic reactions and exothermic reactions. So to begin with our endothermic reactions, these are reactions that absorb heat. These are the factors that influence the rate of a reaction in the temperature. So for example, higher temperatures will increase the rate of the reaction because it provides the energy that is needed for the reaction to occur. So when you're thinking about this, think about increasing temperatures when you're cooking an egg. The heat is absorbed from the pan to cook the egg. Whereas with exothermic reactions, these are the reactions that release heat. The factor that influences the rate of exothermic reactions is the concentration of the reactant. So higher concentrations will increase the rate of the reaction because there is a greater chance that the molecules are going to collide. So for example, the concentration of reactants causing combustion or rain condensation of water vapor into rain releases energy in the form of heat. So really the best way to think about this is endothermic reactions absorb heat and exothermic reactions release heat. Chemical equilibria. A chemical reaction is said to be at equilibrium when the rate of the forward reaction is equal to the rate of the reverse reaction. At equilibrium, the concentration of the reactants and products remain constant. There are 2 different types of equilibrium. We have dynamic equilibrium and static equilibrium. So when it comes to dynamic equilibrium, this is the forward and reverse reactions that are occurring at the exact same time. So a good example to think about this is soda. When it's inside a sealed bottle, carbon dioxide is present in both liquid and gaseous phases. Those are the bubbles that are happening within the soda. These 2 types are considered dynamic equilibrium because the carbon dioxide is dissolved into the liquid form at the same rate as the liquid form is being converted into gas. Static equilibrium is when the concentration of the reactants and products are not changing, right? They're static. An example of this is the weight of the body. The weight of the body is nothing but the amount of gravitational force that is being acted upon it. The gravitational constant is the same as all objects. Therefore, the body doesn't change when it becomes repositioned, right? We still are within that static equilibrium. The position of equilibrium can be shifted by adding and removing reactants and products. If you add a reactant, the position of the equilibrium will shift to the right. Whereas if you remove the reactant, the position of the equilibrium will move to the left. So we talked a little bit before about catalysts, but now we're going to take a little bit closer look at them now. The catalyst is a substance that increases the rate of reaction without being used up in that particular reaction. They do this with activation energy. That is the minimum amount of energy that is used for a chemical reaction to occur in the first place. Catalysts lower the activation energy by providing an alternative pathway for the reaction to occur. So for example, enzymes are proteins that act as catalysts in biochemical reactions. Enzymes are specific to the reaction that they catalyze and are usually named after the substrate that they act upon. Amylase is an enzyme that catalyzes the breakdown of starch polymers and glucose monomers. Now we're going to start taking a closer look at properties of solutions, beginning with polarity of water. Water is really, truly incredible. Water is a polar molecule. That means that water molecules have a slight negative charge at the atom of oxygen level and a slight positive charge at the atom of hydrogen level. The polarity of water allows it to form hydrogen bonds with other molecules. Hydrogen bonds are really weak attractions between molecules. This can either be through cohesion or adhesion. When it comes to cohesion, this is the process of similar molecules surrounding and binding to another molecule. So water molecules can surround and bind with other molecules because of that polarity of water. Water is going to attract water. Whereas with adhesions, this is the process of dissimilar molecules binding with another molecule. So water molecules combine with other molecules because of that polarity. And water is considered really the universal solvent when it comes to a lot of different kinds of reactants and products, meaning that many substances are going to be able to dissolve in water. So solvents and solutes. A solvent is a substance that dissolves in another substance. Water is the most universal solvent, right? We talked about that before. Whereas a solute is a substance that dissolves in a solvent. So sugar is the most common solute that can dissolve in water. So for example, a solution is formed when liquid mixes contains one or more solutes that dissolve in a solvent. Solutes can either be classified as one of two things. They're either hydrophilic, meaning that they are water-loving, or hydrophobic, meaning that they are water-fearing. So for example, a hydrophilic salt is an example of hydrophilic, whereas hydrophobic, when it comes to water, is oil. Salt will dissolve, it's hydrophilic. Oil will not, it's hydrophobic. Solubility is the ability of a solute to dissolve in a solvent. The amount of the solute that can dissolve in the given amount of solvent is called the solubility limit. The solubility limit is also dependent on temperature. So for example, hot water can dissolve more sugar than cold water. So what is the concentration and dilution of solutions? The concentration of a solution is the amount of solute that is dissolved in a given amount of solvent. Dilution is that process of adding solvent to a solution to decrease the concentration of that particular solution. So different units of measures that can be used to express concentration of solution is depending on that particular application. The most common that they use though is called molarity. Molarity is a unit of measure that describes the concentration of a solute in a solvent. Molarity is expressed as moles of a solute per liter of solution. So that is MOL dash or slash capital L. Moles of solute slash liters of solution. Let's talk about a topic you're going to hear in nursing school all the time, and that is osmosis and diffusion. Osmosis is the process of water molecules moving from a higher area of water concentration to a lower area of water concentration through a semi-permeable membrane. A semi-permeable membrane is a barrier that allows some molecules to pass through, but not others. Diffusion is the process of molecules moving from a higher area of concentration to a lower area of concentration. Osmosis and diffusion are both considered passive transport processes. So when you're trying to remember this, remember osmosis specifically refers to the water aspect, whereas diffusion specifically refers to molecule aspects. So we talked about before, osmosis and diffusion are both passive transport processes. However, there are also active transport processes, so we're going to take a closer look at both. Passive transport processes do not require energy. They only require that the molecule is within motion, right? It's moving. So for an example, osmosis is when a plant takes up water from the soil through its roots. Whereas with diffusion is when perfume molecules spread throughout a room. These are both passive transport processes. However, some things need a little bit more energy. They need to be more actively moved. Active transport is a process of molecules moving from an area of low concentration to a high concentration, but they are going to require energy because molecules are moving against a concentration gradient. So an example of active transport is when a cell takes in glucose from the blood. That's going to require energy to make that particular molecule move. So now we're going to talk about one of my favorite subjects, and that is acids and bases and how those two work together. An acid is a molecule that increases the concentration of hydrogen ions in a solution, whereas a base is a molecule that decreases the concentration of hydrogen ions in a solution. So those hydrogen ions are extremely acidic, and if you have too many of them or not enough of them, they can cause a lot of problems. So pH. That is the strength of an acid or base is going to be measured on a pH scale, as you can see here in the slide. The pH scale ranges between 0 to 14. The pH of 0 is going to be the most acidic, whereas the pH of 14 is going to be the most basic. And the pH of 7 is really the most neutral. pH is a unit of measurement that describes the concentration of those hydrogen ions that are going to be found in a solution. The higher the concentration of hydrogen ions, the more acidic the solution, whereas if you don't have a whole lot, the lower that concentration is, the more basic the solution is going to be. Now, in order to balance out solutions, right, to make them more neutral, as more acidic or more basic, we're going to need to have buffers. And a buffer is a solution that can resist changes in pH. Buffers are important because they help maintain the pH of a solution within a certain range. An example of a buffer is blood. Blood has a pH between 7.35 and 7.45, which is maintained by that buffer system. The buffer system is made up of carbonic acid and bicarbonate. Carbonic acid is really a weak acid, and bicarbonate is really a weak base. So by working together, they help maintain the pH of blood within that certain range. And lastly, we're going to take a look at neutralization of reactions. A neutralization reaction is a chemical reaction between an acid and a base. The products of a neutralization reaction is usually water and salt. Neutralization reactions are important because they help maintain the pH of a solution within a certain range. So for example, a neutralization reaction is the reaction between stomach acid and an antacid. Stomach acid's pH is around 0.75, which is really, really low, right? That's very, very acidic. Whereas the antacid has a pH of around 11. That's extremely high. It's extremely basic. When the stomach acid and antacid react, they neutralize one another, and the pH of the solution is brought back more to a more neutral value as opposed to more acidic value. I hope that this information was helpful in understanding chemistry that is going to be on ATI TEAS version 7. If you have any additional questions, make sure you leave them down below. I love answering your questions. Head over to www.nursecheung.com where there is a ton of additional resources available for you when it comes to your ATI TEAS. And as always, I will see you in the next video. Bye!